Looking at solving trigonometric equations for, well, mostly sines, cosines, and tangents. We're going to get something different later. And well, the idea here is to, well, number one, let me go to the graphing calculator. All right. Let's see. Okay, so this is the example we went last time. That was sine 3x equals a -1. And we looked for the solutions within the interval 0 to 2 pi. Let me change the window again. So that's, oh yeah, that's 2 pi. Second, oh no, not second, just graph. And we got three solutions graphically. We also got that same thing algebraically. All right, now we're going to look at another equation that is tangent of the quantity. What's that? Theta minus pi over 2, that is simply, well, x minus second pi over 2. All right, and well, that should be equal to 1. All right, so let me clear, that's just 1. And graph, so this is what we're going to see, and that's in the interval between 0 and 2 pi again. Well, how many solutions would we expect to obtain algebraically based on our picture here? Two. That's because we have 2 points of intersection between the horizontal line y equals to 1 and the tangent line, and the function tangent of theta, theta minus pi over 2. Okay, let's go about this. All right. So first things first, I know this tangent function, it's a composite function because it's not just tangent of theta or tangent of x, you know. It has a little more than just that. It's a composite function. Well, the thing here we need to, number one, what angles have a tangent equal to 1 regardless of the angle? We will deal with the angle later. So number one, the number one thing we need to check is what quadrants contain the tangent function as a positive value. What are those two quadrants actually? For third and first. Okay, sounds good. Okay, third and first. Okay, it's going to be this angle and that other angle. Okay, what is this angle, by the way, in the one in the first quadrant? What angle has a tangent equals to 1? Pi over 4, all right? And of course, the one in the third quadrant, it's a multiple of pi over 4, which in this case is that 5 pi over 4, I believe. All right. That means in this case we will obtain two generating expression, two solutions. Well, number one, just treat this guy as one single term on the one hand. That's going to be theta minus pi over 2 equals to, on the one hand, pi over 4 plus something, and theta equals to, theta minus pi over 2 equals to 5 pi over 4 plus something. What is that something, to fill in the blank? Well, that has to do with the fact that we are going to obtain periodic solutions, you know. We did the same thing with the previous couple of examples last time. However, this time we need to be very, very careful because in the previous examples, we went with the period for the sine and the cosine function, which happened to be 2 pi. That is, evaluate at any angle, add multiples of 2 pi, you end up in the same point. And also, that came from the graphs of the trigonometric functions, and well, in this case, it turns out that the tangent function, it's no longer periodic at 2 pi, but it's rather periodic at pi. And of course, multiples of pi. All right. Well, we want to get the solutions for the theta, not theta minus pi over 2. So what we're going to do here is the following. Let's add pi over 2 and pi over 2 to both sides of both equations. All right, let's see. So that's going to give us theta equals to pi over 4 plus pi over 2. That's essentially, okay, multiply by 4, divide by 4. No, by 2, just 2. And well, that's going to be pi over 4 plus 2 pi over 4. That's 3 pi over 4. Plus pi k. And on the other hand, theta equals to 2 pi over 4 plus 5 over 4. That's 5 pi over 4. That's a 7 pi over 4 plus k pi. All right? So here is the thing. Now that we obtained the two generating expressions, number one, again, these values, these original values that we get as the ones for which we are going to add multiples of pi, those are called the principal values. In this case, that's the 3 pi over 4 and the 7 pi over 4. If you want to label this 3 pi over 4 as PV for principal value, PV for principal value. And well, of course, because the tangent function is periodic every pi units, well, we're just going to add pi, 2 pi, 3 pi, 4 pi, etc. But well, we won't just add any multiples. So we're going to start with k equals to 0. So for k equals to 0, we should obtain the following. That is, theta on the one hand, 3 pi over 4 plus pi times 0. And that's going to give us simply 3 pi over 4. All right? And then the same k equals 0 for the second generating expression. That's 7 pi over 4 plus pi times 0. Well, that's going to give us also simply 7 pi over 4. All right, let's keep going. I know what you might be thinking, but hold on. Isn't this already the two solutions below 2 pi? Well, that could be the case. However, just to make sure about it, go one more value of k. So that is, I'm going to go k equals to 1. Even if it goes beyond the 2 pi interval, just cross that solution, which is what we're going to do here. 3 pi over 4 plus pi times 1, which is simply pi. How about multiply by 4, divide by 4, so we can turn these values into fourths and combine them together. 4 pi plus 3 pi, that's going to give us 7 pi over 4. And for the second generating solution, that's 7 pi over 4 plus pi times 1 times 4 over 4 to combine the fourths together. Okay, 4 pi plus 7 pi, that's 11 pi over 4. Okay. So let's stop here and analyze or assess the results. Number one, 3 pi over 4 and 7 pi over 4, those are two values within the interval 0 to pi. So that's why we will call them legitimate solutions for our purpose. However, well, notice the 7 pi over 4, it's a duplicate of what we get from the second generating expression for the previous value of k. That's something you will see every time you solve trigonometric equations for tangent functions. You will see these repetitions. And well, check this out. This 11 pi over 4, that's a value not within the range, not within the interval 0 to 2 pi. So for this reason, just cross it. That means that if we do k equals to 2, well, this theta would have been the same as before, that 11 pi over 4, and whatever value which is going to be already a really big number which we need to cross out. I'm just going to erase this. All right? We don't need this. So really the two solution set will be theta in curly braces, that's a 3 pi over 4 comma 7 pi over 4. All right, that's final answer. Of course, we're going to verify this couple of results using our graphing calculator. All right, so let's see. Let me divide this window into multiples of pi over 4. So second, pi over 4. Okay, and let's click graph. All right. Let's see this first intercept. So each line right here represents a pi over 4, pi over 4, 2 pi over 4, 3 pi over 4. Well, do you see this intersection between the horizontal line and the tangent function? Doesn't that look like the 3 pi over 4 we just found algebraically? So 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4. Alright, does that look like the solution we also got algebraically? And well, do you see that potentially that 11 pi over 4, which is out of the range 0 to 2 pi, well, we don't want that one. So we just want all the solutions that lie within the 0 and 2 pi interval. Alright, so let's see. Let's go back and look at another example. Okay, so we're going to move on to exercises that are going to be a little more involved in terms of the algebra used here, all right? So this time we're going to look at this equation that looks in a quadratic pattern. Remember those equations we solved when we looked at, what was that, logarithmics and exponentials? So we also solved equations that look like quadratics back then. You know, when we solved something like 2e to the 4x plus 7e to the 2x plus 1 equals to 0. Well, then we say that u equals to e to the 2x, and then 2u squared plus 7u plus 1. We turn this equation into a polynomial equation, a quadratic equation in quadratic form. Solve the quadratic equation for the value for u or whatever. Well, in this case we use u. And then once we solved for u, we went back and substitute for u, which is e to the 2x, and we solved two baby exponential equations. So some similar pattern is going to be here, all right? So except that we won't have logarithmics or exponentials. We would rather have about u equals to cosine theta. Setting u equals to cosine theta, well, this will turn the equation into this one. 2u squared minus u minus 1, and set that equal to 0. All right? So here we need to find the best way to solve that polynomial equation. Well, it's a trinomial, and we will have to solve either, well, not the quadratic formula. I think that's overkill, maybe factoring. So we should factor the way we factor trinomials when the leading coefficient is not equal to 1. We can use the diamond method or the slip and slide method. If you know the guess and check method, be my guest, use it as long as it works for you. The pizza method, well, you want to know those methods I'm mentioning, well, see me after class, or yeah, okay. So I'm going to go with the diamond method, which is for the most part the most standard way to solve this kind of problems. So what do? Multiply the leading coefficient times the independent term. That's going to give us a -2, and bring down the leading coefficient. All right. Then from here, we will find two factors of -2 that add up to -1. Any ideas of what are those two numbers? Factors of -2 that add up to -1.
-2 and 1.
-2 and 1. Okay, sounds good. Sounds like a plan. -2 and plus 1, right? Because -2 times 1 is -2, and -2 plus 1 is -1, indeed. What are we going to do with these two numbers? Careful, not like the double bubble method we did before. We're going to split these two, -2 and 1, and simply, actually it's a -2u and 1u. So that means, well, 2u squared minus 2u plus u minus 1. Set that equal to 0. All right. Then, since we have 4 terms right here, how about we use factor by grouping? That's the method we go every time we have 4 terms. So by grouping 2 by 2, and then what we do here is find the greatest common factor of every group. That is, in this case, 2u times u minus 1. And well, here between u and -1, there's no common factor. Well, actually, there is. There is a common factor between these two terms, right? Between u minus 1. What do they have in common? The number 1, right? And well, I know it's kind of silly to write that 1, and that's because, well, that's because we need to see this new, or this second greatest common factor, which is the u minus 1 and the u minus 1. Factor out the u minus 1 to get 2u plus 1 and set that equal to 0. All right. So let's see. That means by the zero product property, u minus 1 equals to 0, or 2u plus 1 equals to 0. All right? Well, from here, how about we solve for u's? U equals to 1, 2u equals to negative 1, and u equals to negative 1/2. All right. Let's see about it. So now that we solved the problem in the world of u, let's go back to the original world, which in this case it's the world of trigonometric functions. Recall that we did a substitution for u equals to the cosine theta. All right, let's go back and substitute for u. So cosine theta equals to 1 and cosine theta equals to negative 1/2. So we will really solve two equations into one single problem. That's because we end up having two factors because of a quadratic equation, right? Because it's in quadratic pattern. Well, so let's solve one equation at a time. So let's come up with a couple of Cartesian planes. One Cartesian plane for cosine equals to 1. Okay, so let's solve that equation. Well, what values between 0 and 2 pi have a cosine equals to 1? Zero? Just 0? It looks like just 0, right? So 0. And here let me label theta equals to 0. Let's do the same for negative 1/2. Be careful here, because now what quadrants will have a negative value first of all? No, which quadrants have a negative value for cosine? You say second quadrant, what else? Where else? Third quadrant, right? So that is the order pairs containing a negative 1/2 in the x component, because, well, that's how these trigonometric functions are related to the points in the unit circle, that is the x coordinate. Now the question here is, what are these angles right here? For the one in the second quadrant, what angle has a cosine equals to negative 1/2 in the second quadrant? To pi over 3, it looks like it is 2 pi over 3. What about the one in the third quadrant? 4 pi over 3. Thank you. 4 pi over 3 and 2 pi over 3. Oops. All right, and well, that's theta equals to 0. All right, so we already have the three solutions, the three principal values for the solutions to this equation right here. All right, so let's see about this. Let's go back, let's go to the top and write the three expressions, the three generating solutions. So number 1, and that's going to be 3 because we had 3 solutions, one from from the first equation and the other one from the second equation. All right, let's see. So this will be, first of all, theta equals to 0 plus 2 pi k. On the other hand, we're going to have theta equals to 2 pi over 3 plus 2 pi k. And lastly, theta equals to 4 pi over 3 plus 2 pi k. Well, we don't have any shiftings or transformations for these trigonometric functions or equations that we're solving for the angle. So we will just generate some values for OK. How about for k equals to 1? I mean, k equals to 0, not 1. We start with k equals to 0. Okay, let's generate solutions. Well, the first theta will be 0 plus 2 pi times 0. Theta equals to 2 pi over 3 plus 2 pi times 0. Theta equals to 4 pi over 3 plus 2 pi times 0. So let's evaluate or simplify these expressions. Of course, we are evaluating k at 0. That's going to get zeroed out. All right. Theta equals to 0. Theta equals to 2 pi over 3. And theta equals to 4 pi over 3. All right. Let me draw a line here so we can distinguish between the process for k equals to 0 from the process of evaluating for k equals to 1. And well, you will find out weird stuff when we evaluate this for k equals to 1, because check this out. That's going to be theta equals to 0 plus 2 pi times 1 for the first generating expression. And then theta equals to 2 pi over 3 plus 2 pi times 1. And theta equals to 4 pi over 3 plus 2 pi times 1. Notice the result of combining or of simplifying these three expressions will be values that are either 2 pi or larger. And well, in this case, we don't want any values that reach even the 2 pi. So we just want inclusive for 0, the lower limit or the lower bound, and exclusive for 2 pi, the upper bound. All right, so that's going to give us on the one hand the 2 pi. This is going to give us 2 times 3, 6 plus 2, that's 8 pi over 3. And that's 2 times 3, 6 plus 4, that's 10 pi over 3. And notice how all these values go beyond the interval 0 to 2 pi. All right? So the only legitimate solutions are going to be the ones that we listed for k equals to 0, which at the same time happen to be the principal values for the solutions of the equations. All right, so let's call this a solution set. That's theta equals to 0, 2 pi over 3, 4 pi over 3. That's one more equation here. All right. Let's see about another example. Let's see how many more we have right here. Okay, letter E. So letter E, number 1, it's a quadratic equation. That's to begin with. Number 2, this equation, it's unfortunately about to give us a lot of trouble. Yes, however, we should be able to use the correct trigonometric identities to simplify this equation in a way that it is convenient, so we can get the correct, or rather the easiest approach, or an approach that we can actually, well, not necessarily the easiest approach, but rather an approach for which we can proceed algebraically and not in a different way. What do I mean by that? Well, every time we solve trigonometric equations, number one, these equations have to be in terms of only one type of equation, or rather function, preferably like either an equation in terms of all cosines or an equation in terms of all sines maybe, or all tangents, etc. That's number one. And well, I think we're seeing an issue here with that. We have a combination of cosines and sines. All right. Now, what else? Also, we need to make sure the equations or all the terms comprising the polynomial, the trigonometric polynomial, have the same angle. In this case, what do I mean by the same angle? That is theta, theta, theta. If I have a combination of thetas, 2 thetas, 5 thetas, no, it's not going to work. We won't be able to proceed algebraically with an equation like that. And the reason why I am going over this is because check this out. So we should use trigonometric identities to rewrite the left-hand side of the equation. And well, let's see if this part of the left-hand side reminds you to anything. Does that remind you to anything? In fact, we did this recently. Cosine squared minus sine squared. That's an identity. Which one is it? What is that equal to? 1. It would have been 1 if we had the plus in between, right? 2 cos theta. I think it's just cosine 2 theta here, right? All right, so check this out. So cosine 2 theta plus sine theta. We have double trouble here. Number one, we have 2 different trigonometric functions, all right? And also we have 2 totally different angles. One term contains a 2 theta and the other term contains a single theta. So I don't think there's a way we can go about this one. So no, we have to take a different approach in this case. Well, the fact that we use the identity cosine 2 theta, what kind of identities were those? Does anyone remember what kind of identities are those? It's a double angle. Well, yes, we use a correct identity because cosine squared minus sine squared equals to cosine theta. But you might want to recall something. Well, number one, sine 2 theta equals to sine theta cosine theta. But we're not going to use this one. This is just to recall the identities. Well, what about the other identities, the ones for cosine 2 theta? Number one, well, the one we began with, that's cosine squared minus sine squared. But there were 3 equivalent identities for the double angle for cosine 2 theta. For the double angle for cosine rather. And the other 2 alternatives, one look like this: 2 cosine squared theta minus 1 and 1 1 minus 2 sine squared theta. And again, as we described before, you might want to have an equation in terms of one single trigonometric function. So how about in terms of all sines, and also in terms of just one single type of angle, not 2, not 3. All right. We could actually well, how about, yes, to begin with, let's write it as cosine 2 theta plus sine theta equals to 1. And well, this cosine theta, have about everything in terms of sine. That is 1 minus 2 sine squared theta plus sine theta equals to 1. And now, do you see how we have an equation in terms of number one single function, that is the sine function, and the angles are what? Just theta, not 2 theta, not mixed with another 2 theta or a 3 theta like what we have in the previous step. No, it's not anymore that kind of equation. So now we're safe to work with this equation. Number one, subtract 1 from both sides. Oh, that cancels all ones. And check this out. That's going to leave us with negative 2 sine squared theta plus sine. Theta equals to 0 actually. And while this is a polynomial equation in terms of trigonometric functions that we can solve, that we can factor in terms of a GCF. We don't need a factoring for a trinomial because we don't have a trinomial, nor we need the quadratic formula. So we can factor out 1 power of sine. That's going to leave us with 2 sine, or rather negative 2 sine theta plus 1. All right, set that equal to 0. So on the one hand, number one, using the zero product property, that's sine theta equals to 0, and on the other hand, negative 2 sine theta plus 1 equals to 0. All right? So those are the two baby equations that we need to solve. So again, we are solving two equations in a single problem. So how about, okay, sine theta equals to 0 is already sine theta equals to 0. Okay, let's isolate the trigonometric function on the second equation. That's to give us a negative 2 sine theta equals to negative 1. And dividing both sides by negative 2, that'll give us sine theta equals to 1/2. Sounds good? So let's, number one, draw the Cartesian plane for the angle of theta equals to 0 degree, or rather, no. What trigonometric or what angles have a sine equal to 0? What's that again? Well, between 0 and 2 pi, but not 2 pi.
0 and pi.
0 and pi, right? So in this case, that's a 0, that is sine equals to 0, and also sine equals to 0. So two values, right? Well, the order pairs 1, 0 and negative 1, 0. We can complete the order pairs here. And well, that means, okay, theta equals to 0, theta equals to pi. What about for the second order pair? I mean the second equation, not the second order pair. Number one, we want to know the angles. We want to find out what angles have theta, or have a sine equal to 1/2. Number one, it's a positive 1/2. So what quadrants are going to be positive for sine? 1 and 2. All right, the order pairs having the y value to be a 1/2. Okay, what are those angles, by the way?
Pi over 6 and 5 pi over 6.
Pi over 6, pi over 6, and 5 pi over 6. All right, multiples of pi over 6 in this case. All right. Okay, so I guess we already have what you call the principal values here. So let's see, let's list them. So number one, oh my God, I'm gonna need a lot of space here. Okay, usually I do this horizontally. This time I'm gonna go vertically. So I'm gonna go on the one hand. So, whoops. Theta equals to, number one, 0 plus 2 pi k. Theta equals to pi plus 2 pi k. Theta equals to pi over 6 plus 2 pi k. And theta also to be, what's that, a 5 pi over 6 plus 2 pi k. All right? So let's compute some values of k until we reach to the maximum of 2 pi. Well, let me call this the column for k equals to 0. And well, this time I'm just going to do the calculations like up in the air. I'm not going to plug in the values. Well, you know what I'm going to do then? What the hell? So let's make the table real quick. And let's see. So for k equals to 0, we're going to have theta equals to 0 plus 2 pi times 0. That's simply going to be theta equals to 0. All right? What about for the next angle? So that's theta equals to pi plus 2 pi times 0. That's simply pi. All right? Those two angles so far are angles that lie within the interval 0 and 2 pi. Theta equals to pi over 6 plus 2 pi times 0. That's simply pi over 6. And theta equals to 5 pi over 6 plus 2 pi times 0. What's that? Also 5 pi over 6. Okay, so far we have angles that are within the interval 0 to 2 pi. All right? Let's see the story for k equals to 1. And I think after doing a couple of examples, you can see the pattern and you will see how we're going to get past the interval 0 to 2 pi. All right? So, for k equals to 1, how about theta equals to 0 plus 2 pi times 1? Well, that's theta equals to 2 pi. Well, we don't want the 2 pi in the solution set. So that's going to be already a number that we will cross out. For the next value of theta equals to 2 pi equals to pi rather plus 2 pi times 1. And while combining these numbers together, that's 2 pi plus pi, that equals to 3 pi. And well, that's a number also outside of the interval 0 to 2 pi. And one more value, theta equals to pi over 6. Let's go with the multiples of pi over 6. That's 2 pi times 1. But we need to combine fractions. Well, that's 2 times 6. That's 12 plus 1. Is that 13 pi over 6? And that's also a number that lies outside of the range 0 to 2 pi. And last but not least, theta equals to 5 pi over 6 plus 2 pi times 1. Well, in this case, well, that's 2 times 6, which is 12 plus 5. Is that theta 17 pi over 6. Assessing these values, all these values should be crossed because they are outside of the 0 to 2 pi interval that we are required in instructions. So what we're going to do here is just call this a solution set only for the values that lie within the interval 0 to 2 pi, which is 1. Whoops. That's 1, 2, 3, and 4. Only those 4 are the solutions within the interval 0 to 2 pi. So theta equals to, what's that? First solution set. That's theta equals to 0, pi over 6, pi, and 5 pi over 6. Those are the solutions here. Whoops. All right.